Good morning, guys. Just responding to a couple of your posted questions about question number 3 from the classwork. So I'm going to walk you guys through it a little bit and hopefully give you a little bit more direction with all this optimization stuff. I know it could be difficult to learn on your own, so let's go through number 3 together. All right, so number 3 says a cylindrical canister is closed at both ends. That just means it's solid and you have this full can, and the can has to have a volume of 16,000 cubic centimeters, okay? This is going to be your constraint, okay? That is the volume that's not changing. It's constantly going to be 16,000. You want to find the minimum surface area, okay? You want to minimize the surface area. So that is going to be the one that you want to obviously minimize, but that's going to be the one that you take the derivative of. That's going to be the one that we're going to take the derivative and set the derivative equal to 0 because that is going to be our minimum. So let's start with our formulas. First of all, the volume for a cylindrical can or cylindrical canister is volume equals pi r squared h. We know that the volume is constantly 16,000. So we know that we have 16,000 equals to pi r squared h. Again, this is your constraint. This is what is staying constant. That never changes. In addition to that, we have a formula for surface area. Remember the surface area, if you see it in the video that we shared from YouTube, or you can look it up online. Surface area for a can consists of two circles, so 2 pi r squared, that covers the top of the canister and it also covers the bottom. So this guy up here and this guy up down there, okay? In addition to that, you also have the part or the lateral side that is 2 pi r h, okay? That is 2 pi r h. That's the part that goes around that area there. Now, if this is the one that we want to take the derivative of, this is the one that we want to minimize, there's a problem because this is in terms of two variables right now. So that makes me a little bit sad. So here's what we're going to do. We're going to take this guy, the constraint, okay? And we're actually going to solve that constraint for one of the variables. Now I'm looking at this formula here and I'm saying to myself, you know what? It's going to be a lot easier to solve for h because h doesn't have any exponents, there'd be no square roots. This would be nice and pretty. So if that's the case, if we divide both sides by pi r squared, we get that 16,000 over pi r squared is equal to h. Notice I can now take this expression for h and substitute it right in there, okay? So now what we have is surface area is equal to 2 pi r squared plus 2 pi r, and now we're going to substitute in 16,000 divided by pi r squared, okay, right in for where we saw h. Notice now this entire expression is written all in terms of r. There are no h's here anymore, okay, it's all in terms of one variable, so that works out really well for us because now we can clean this up and then we can take the derivative. So if that's the case, the surface area is equal to 2 pi r squared plus, let's just clean this up. Note that the pi's are going to cancel and 2 times 16,000 is going to be 32,000. And also note that your r and your r squared will cancel and you'll be left with an extra r. Now, I'm no longer upset. I'm rather now happy because this is all in terms of one variable. And now that it's all in terms of one variable, we can take the derivative for the surface area. Just using your power rule, we have 2 times 2 is 4 pi times r. Note that this term here is really 32,000 r to the negative first. So if that's the case, we'd have minus 32,000 over r squared, really r to the negative second, but it's moved down. Again, because we're trying to minimize, that means that the derivative should equal to 0. So I'm going to set the derivative equal to 0. That means that we have 4 pi r equals to, just moving this guy over to the other side, 32,000 over r squared. We can put this over 1 and cross multiply. So that means that we have 4 pi r cubed is equal to 32,000. Okay? And therefore, we can actually solve for r by dividing both sides by 4 pi. Divide both sides by 4 pi. Okay, and that is going to give you, I'm just going to move up there, that r cubed is equal to 8,000 over pi. All right, you can take a cube root, so r is going to equal to 20, I believe, over pi. You have to forgive me, I don't have my calculator with me right now. 22,333, that looks good to me. Okay, so the only thing that's left over here, guys, is that we just need to make sure, or you need to check, that that r provides a minimum. So let me just go through some of the constraints in terms of like, what can r be as a smallest r and what can r be as the largest r. If you look at this formula here, suppose that r is really small. If r is really small, that means that it's going to be close to 0. So the smallest value your r can take on is 0. Let's suppose r is actually really big, which means that h would have to be really small. If h is really small, that means that it's close to 0. That means that 16,000 would have to be really close to pi and r squared. Notice that the h would be really close to something very small, so it's kind of insignificant. We actually don't need to consider it to find the maximum value for the r. Okay? So if that's the case here, we have 16,000 divided by pi is equal to r squared. That means that your r, or the biggest value for r, is going to be the square root of 16,000 over pi. So r, when we're checking, has to be somewhere between 0 and the square root of 16,000 over a pi. This value here, the 20 cube root of pi, that will be in the center. When the answer key is posted later today, you will see that, it's written in decimal form, and it is in between those two numbers. You then just need to verify using the derivative of the surface area, okay, to make sure that this is a minimum. So if I just briefly use a value like 1, I know 1 is in this area. Again, you can use your calculator just to show that when r is equal to 1, it is in this area, but that will be a negative number. If you choose a value for r in this area, that will produce a positive number, giving you a minimum. That means that the radius that will produce a minimum surface area is that value there. Again, on the answer key, it's going to be written in decimal form, but just to help you guys out, I'm leaving it in the fractional form. But they do want you to actually find the surface area of the canister. So if that's the case, just don't forget to take this radius here that you found, okay? Don't forget to just take that radius that you found down there, and you want to plug it back into your surface area formula right there just to get the value. I'm going to stop the answer key for this question here, and the later answer key will be posted today at 3 to give you some idea, but hopefully this video kind of helps you explain it out a little bit. Let me know if you have any further questions.